Okay, good morning, everyone. Hope you had a good weekend. Today, we are going to be starting our exploration of evolutionary epidemiology. This is a pet favorite of mine. As some of you know, I'm interested in understanding infectious diseases and how they spread and how they evolve, and in turn, also how they affect the evolution of their host populations. So this is my main area of research interest. So we're going to be delving into this a little bit today and using some of the techniques that we've learned recently to do with adaptive dynamics to try to understand how we can predict key traits related to pathogens that cause infectious diseases. How do these key traits evolve? Okay, so most of our focus so far, when we've been talking about adaptive dynamics as a framework for modeling evolution, has been focusing on this model of intraspecific competition, which we've looked at many times now. So that's all really about competition for resources between individuals of the same species, okay? So these resources could be things like food or territory or mates, anything that might be something that is a source for a competition, so there's some limitation there. This is, of course, just one particular type of biological scenario. It's very general, but it also focuses on this idea just of competition between individuals within a species. There are lots and lots of different examples across evolutionary biology, though, that encapsulate many different types of traits and interactions, both within species and between species, okay? So, for example, we can apply adaptive dynamics to try to understand things like the evolution of sex ratio. We touched on this a little bit when we did evolutionary game theory, but we can do it in a slightly more robust way here. We can also look at things like the evolution of mate choice. You know, we talked a little bit about, you know, why should, say, peahens prefer peacocks that have these beautiful displays, okay? This comes into the realm of sexual selection. So who should you mate with and how often? Ideas about mutualism as well. So many species are mutualistic towards each other. Think about things like plants and pollinators. Even elements of your gut microbiome, friendly bacteria can help protect you from disease and things like that. Evolution of toxins or antitoxins, particularly with, say, plants protecting themselves against herbivores that might try and eat them. Evolution of body size as well. What is an optimal body size, or might there be many different body sizes that can coexist within a population? We talked before in evolutionary game theory about cooperation and cheating, but again, we can think about the dynamics of these processes more when we talk about adaptive dynamics. Mimicry as well is another example. So, you know, butterflies can put up these patterns to advertise to predators that maybe they're poisonous. Some butterflies can try to mimic those even though they aren't poisonous. We can also see mimicry with things like cuckoos that try to match the egg patterns of their host nests. Okay, so lots of examples of mimicry as well. And then we're going to focus today and on Wednesday on infectious diseases. Like I said, this is my pet favorite. Infectious diseases actually do often span into many of these other aspects as well, because infectious diseases are found throughout the natural world. So they can often tell us things about, say, mate choice or mutualism as well. But we're going to focus on more simple examples, just thinking about how, to start with, how does the level of virulence, which is the sort of damage done to a host, how does this trait evolve, okay? This all comes under the realm of something called evolutionary epidemiology. So epidemiology, the study of diseases, or in this case, infectious diseases. And so we're going to be thinking about how do these infectious diseases evolve, okay? So we're going to start with a bit of an introduction about infectious disease models. For those who did Math 360, some of this will be familiar. If you've not done Math 360, then they'll be a little bit unfamiliar, but we'll just go over some of the basics. We're going to be talking about these foundational models of epidemiology, which are called compartmental models. You might have heard of something called an SIR model before, perhaps, especially in the context of something like COVID. We're going to talk about a little bit briefly about the ideas of transmission modes, but this idea of density-dependent transmission is not going to be a key focus for us. I mentioned this idea of virulence before. Key other aspect of this is the average infectious period, and we'll talk about the basic reproduction number as well. And so by the end of today, hopefully you should be able to construct at least these simple models of infectious diseases and also start thinking about how we analyze evolution of infectious diseases as well. Okay, so like I said, we have these compartmental models. These are kind of the foundation of modern epidemiology. And they're called compartmental models because what we do essentially is we break down the population into these different compartments, okay? So we treat people based on their infection status typically, but there could be other compartments that maybe deal with something like age or vaccination status, or whether you're asymptomatic or symptomatic. You can kind of build up the complexity of these models, okay? So the simplest, or one of the simplest early versions of this was known as an SIR model. And we split the population into three possible classes, S, I, and R. And then we think about transitions between these classes. And these classes, remember, represent disease statuses. So what's the first one? So S are all individuals who are susceptible. In other words, they're uninfected. They're uninfected, but they can be infected, okay? That's the first class. We then have a class of infected individuals. And in this case, we're going to assume that once they get infected, they're immediately infected. There's no latent period that they have to go through. You could do this by having something called an SEIR model, which is an exposed class. We're also going to assume that they're immediately infectious. Okay, so they can infect other people when they're in this class as soon as they enter it. And then finally, we have a recovered, or sometimes called a removed class. I'll refer to it as a recovered class here. Like I said, there are many different ways in which one can construct these models. A recovered class here is, as it suggests, people who have had the disease who have now recovered from it. In this particular example, there's no arrows going back towards S or anything. So this is actually representing a case where there is recovery and a buildup of immunity to infection. That means they can't be infected again. Okay, so lots of examples of this, things like measles, for example. So this kind of compartmental model was first established back in the 1920s by William Kermack and Anderson McKendrick. And they wanted to try to model deaths due to a plague epidemic in Bombay. And this little figure here is actually taken from their paper. This is their deaths going up here. The little dots are there. The black dots here are what the data suggest. And then this curve is what came out of their model when they chose suitable parameters for their model. And you see it's a pretty good fit. You know, you've got to think about all the complexity that exists in human populations, right? You know, this isn't taking into account sort of, you know, household contact patterns, or the fact that, you know, you've got young people and old people, and they may have different susceptibilities, their lifestyles, all of these different things. We can actually make some pretty good predictions with these relatively simple models. And it's why they, you know, continue to exist today. And these are the foundations of the kinds of models that we talked about during COVID-19, okay? Often they have these additional things, you know, extra complexities ramped up on them, but you can get a pretty good prediction even out of these relatively simple models. Yes?
Can I ask what like the empty dots were?
Oh, the empty dots are just from their curve. So this is sort of pre-computer days where having to you know, work out where these things are and then draw the line through them.
Right.
Yeah. Okay, so let's talk about another type of compartment model. We're going to focus on something called an SIS model for our analysis, just because it's a little bit simpler. We don't have to deal with this third recovered class. So this is a susceptible, infected, susceptible model. So its transition diagram looks like this. We have our S and our I classes, and we can move between them like this. There's no third R class here. So what this is really assuming is that, you know, everyone starts off susceptible, they can get infected, they can recover, but when they recover, they immediately become susceptible again. So there's no buildup of immunity. So this is a good model for many sexually transmitted infections. In fact, that there's no long-lasting immunity to many sexually transmitted infections, things like gonorrhea and chlamydia. Also in invertebrate populations as well, things like insects, where they don't necessarily have any sort of long-term buildup of immunity, they immediately become susceptible again. So this applies to many, many infectious diseases. What do our equations look like? Well, we have a system of two nonlinear ODEs, the SDT and the IDT, where S is going to be the density of our susceptible hosts and I is the density of infected and also infectious hosts. And then we're going to assume that there is some birth rate, which I'll call B as a function of S and I. The birth rate for our host population. We then have our infection term, which is this beta SI, minus beta SI. So beta here is going to be our transmission rate, sometimes called a pairwise transmission rate. And what this is really doing, this is telling you about the rate of contacts that we'd expect between susceptible and infected individuals. Okay, so beta captures things like the probability of transmission, but also contact rates as well. And then it's based then ultimately on the density of our susceptible and infected hosts. All of these models, incidentally, they come from sort of well-mixed populations, is the kind of idea here. They come from gas models. You think about molecules moving around in some container, and the probability that any of those two molecules kind of come into contact is based on the densities of those two types of molecules. Okay, so that's our infection term. And in fact, what I'll do is I'll write our infection term here, just so we can keep track of things. So individuals go from this S class to this I class. They get infected at this rate. There's no loss of individuals here. It's just a transition. We're also going to assume that there is recovery. And once they recover, they become immediately susceptible again. This is going to be occurring at a per capita rate gamma. Gamma is going to be our recovery rate. And then we're going to assume that there is a mortality rate, per capita mortality rate D. This is our sort of natural background mortality rate. You can think of this as everything other than our infectious disease that we care about. The last thing to do then is we need to balance our terms in the dI/dt equation. So we've already had our beta SI, which is our infection term. And then here, we're going to have our recovery rate, gamma. Our infected hosts are going to have the same background mortality rate D, but then we're also going to assume that they're going to have an additional mortality rate alpha. And this all gets multiplied by I. So this alpha, we're going to refer to as a sort of disease-associated mortality rate, which is usually referred to as virulence. There are different types of virulence, but for the purposes, unless I state otherwise, we'll refer to virulence as being the mortality rate. Okay. Any questions on this? Yeah.
So in the first model is the fourth, sorry, not first model. In the first equation is the fourth term just talking about the death rate that's not related to the disease?
Exactly. Yeah. So, you know, getting hit by a car, it could be anything else. It could be, if it's an infectious disease, it could be cancer or any other mortality, basically. There are models that you can do without these dynamics. Part of the reason we have these dynamics in here is that there's some turnover of the population in the background. We don't want there to be sort of hosts that live forever. Yes?
And then could you just explain the second term in the second equation again, please?
Mm-hmm. Yep, so this term in the brackets?
Yeah.
Yep, so this is essentially the loss from our infectious class.
Mm-hmm.
So you can think of this as everything that's flowing into our infection class, and this is everything that's flowing out. Okay, so what flows out of our infection class? Well, people who recover, people who die naturally, and people who die from disease.
Right.
Yeah. And note that this gamma they flow back in this way, but for the D and the alpha terms, they just kind of leave the system.
Mm-hmm.
So one way of extending this sort of transition diagram, if you like, is that there would be a B term that comes in. So this would be my B of SI here. I would have this beta SI would be my infection term. I would have gamma I here as my recovery. And then here I would have DS and D plus alpha I as my loss terms. Yeah, so another way of thinking about these kinds of compartmental models is almost like there's buckets and there's pipes connecting those buckets, and there's a certain amount of liquid in those buckets that corresponds to the density of the population. And then they're kind of being pumped either into these buckets or between the buckets and then out of the buckets. And that's kind of, you can think of these arrows as being like pipes.
Mm-hmm.
Yeah. Any other questions? We'll move on. Okay, so one of the things this model assumes is that transmission is density dependent. What that really means, like I described, is that we've got individuals moving around at random. They come into contact with each other based on the density of different types of individuals in the population. And this gives us our transmission term or infection term, beta SI. There are different ways in which we can describe that transmission, but this density dependent one is one of the simplest. Another way we can think of this is we can write this as lambda I. So lambda of I, where lambda of I is our force of infection. Okay, so if I was to zoom in here, just to sketch this. What this basically says is our force of infection under density-dependent transmission increases linearly. Beta is just a constant. So we wouldn't expect the probability of transmission to necessarily increase, but you maybe expect the contact rate to go up. So people are more closely packed in. Think of something like influenza. People are more closely packed in a classroom, say, then it's much more likely that people get infected, right? There's a higher density of individuals. There are many cases where you don't want to have this kind of transmission, maybe something like sexually transmitted infections, where say like in a city, you wouldn't necessarily expect there to be, a city of 10 million people versus a city of 1 million people. You wouldn't necessarily expect the sexual contact rate to be 10 times higher in the city that has 10 million people. So sometimes for different infectious diseases, you have to account for these slight differences. Okay, the other sort of key parameter that we have, or one of the other key parameters we have in our model, I mentioned this recovery rate gamma, positive. What this essentially assumes is that the time spent infectious, which is known as our infectious period, is exponentially distributed. And it's exponentially distributed with a mean 1 over gamma, and variance 1 over gamma squared. This means that our average infectious period, so how long you would expect to be infectious for on average, is 1 over gamma. Now, I haven't actually included any units here. Typically, I haven't stated whether this is measured in days or weeks or months, but you would typically have sort of gamma as a rate per unit time, and then 1 over gamma is just going to give you a time period, therefore. Okay. One of the problems here is that some infections last a very long time, some will last a lot shorter time. So this isn't necessarily a good model for all pathogens. So why might this not be a good model for some pathogens? This idea of some infections lasting a very short time and some lasting much longer. Yeah.
Is it because some pathogens might like mutate or something? So
that's possible. I mean, one of the most obvious one here is that many pathogens, they might just have a very narrow window of infection. Okay, so because these rates here are they're exponentially distributed, it's basically saying some people recover, almost immediately, and some people will take, a very, very, very long time to recover. In fact, many cases you might just, there maybe people are infected on average for 7 days, but they never recover before 3 days, and then you never recover after 20 days, and therefore it's much more tightly condensed. Okay, so the sort of answer here is that some pathogens have a narrow infectious period. Okay, so before we need to sort of move on to our pathogen evolution, as with any sort of adaptive dynamic scenario, we need to focus first on our ecological dynamics, or in this case, we usually refer to them as the epidemiological dynamics, but they're the same thing, essentially. For simplicity, we're going to assume that there's no recovery, just because this makes the math a bit easier. And we're going to assume that the birth rate is given by this logistic-like term here. B is going to be our maximum birth rate. N is our total population size. We assume that only susceptible individuals, so infected individuals, are not going to be reproducing here, and that there's some density-dependent parameter Q. This Q is essentially controlling the strength of density dependence on births. In other words, the more individuals there are in the population, the fewer resources there are to produce new individuals. Okay.
So here, S and I are the number of individuals, not the density anymore?
They are densities. Yeah. So often people refer to for ease, people often say population sizes, but they are densities essentially. Yeah. Okay, so it's possible under this sort of these assumptions to show that the system has 3 equilibria. I'm not going to go through this. We've done examples of this before. I would encourage you to have a go at trying this in your own time to find out what the 3 equilibria are and check that you understand how to get there. One of them is a trivial equilibrium at 0, 0. If no one's around, nothing happens. So this is a trivial. In other words, the host and the pathogen are both extinct. we have another equilibrium at B minus D over BQ, 0. And this is often referred to as a disease-free equilibrium. Note, for this is only valid for B greater than D. Well, B is telling you something about your birth rate, and D is telling you something about your death rate. We need to be having enough births to counteract deaths in order for our population, our host population, to be viable in the absence of disease, okay? So this disease-free equilibrium, I will usually abbreviate to DFE. Then finally, there is a slightly more complicated equilibrium with both our host and pathogen present. This is alpha plus D over beta for our susceptible class. That's not too bad. It's a little bit messier for our infected class. B minus D, all in brackets, times by beta, minus BQ times by brackets D plus alpha, all over beta times by beta plus BQ. Again, I'm including this so that you can check your working and practice doing this, okay? This is known as our endemic equilibrium. Or sometimes referred to as EE. Endemic here is basically just saying that it's being maintained in the population. Contrast to an epidemic, which is sort of an outbreak. You saw that outbreak at the start with the plague curve. That was sort of a characteristic epidemic curve. It goes up, it peaks, it comes back down again, but it's gone down to 0. Here, something that's endemic is basically saying it's staying in the population. Again, for this to be biologically plausible, this numerator here has to be positive. It's always worth remembering that we should check whenever we get any of our equilibria, we need to think about when are they biologically realistic. In other words, when are they, in most cases, non-zero or non-negative. Okay, we can do our usual linear stability analysis. And we do this on all of our equilibria to find out all conditions when they're stable and what kinds of stability they have. I'm just going to focus here on the disease-free equilibrium. Okay, so what happens if we calculate our Jacobian at the disease-free equilibrium? Again, this is a good exercise for you to do. Find our Jacobian and then substitute in our disease-free equilibrium from the previous slide. What do we get? We get something that looks like this. So we have D minus B in our top left element. Top right, we have minus S star times by brackets BQ plus beta. In the bottom left, we have 0. And in the bottom right, we have beta S star minus D plus alpha. Sorry, minus alpha. What I've done here is I've substituted some of the S stars and I stars that I would have had in. I've left these S stars in here just for ease, okay? So here I did some substitutions. For example, there's an I star here, and the disease-free equilibrium, this is 0, so this is a nice substitution to make. Sometimes it's good to do a little bit of substitution, but not do all of your substitutions, okay? Okay, well, if we want to look at the stability of our disease-free equilibrium, one way you can do that is use the Ralph-Hurwitz conditions. So we can look at the trace and determinant. So the trace of this is just going to be D minus B plus beta S star minus D minus alpha. And our determinant is going to equal, I'm going to put it as minus B minus D. And minus it's B minus D. And then the bottom right element, beta S star minus D minus alpha. Okay, so we can think about our Ralph-Hurwitz conditions to think about the stability. Remember, if our trace is negative and our determinant is positive, And this tells us that the real parts of all of our eigenvalues have to be negative, and therefore any small perturbations will decay away, and our equilibrium is going to be locally asymptotically stable. Locally asymptotically stable. Okay. So one thing we can zoom in on here is just this second condition here with the determinant, because it tells us something interesting about the infectious disease. Okay, that'll become apparent in a moment. If we assume that our population is viable, in other words, in the absence of disease, well, regardless of whether disease is there or not, B is greater than D, in other words, our host population can survive. This disease-free equilibrium is going to be unstable. Let's consider our determinant condition. What happens if our determinant is negative? What was our determinant up here? Well, we've just said we're going to assume that B is greater than D. In other words, we have births greater than deaths. So this term here is positive. We can just divide through by that. That's fine. We therefore need this minus sign we can multiply throughout by this minus sign as well. So it's going to flip this round. We end up with beta S star minus D minus alpha has to be positive. Okay. So all I've done there is B minus D is positive, divided by that. We've got a minus sign there, so it's going to flip the inequality round. We could do a little bit of rearranging here. If we take the D and alpha over to the other side and then divide by them, where D and alpha are both positive constants, so we can do this. We get that our disease-free equilibrium is going to be stable if this quantity here, beta S star is our disease-free equilibrium for our host population, divided by D plus alpha is greater than 1. I'm going to call this quantity R naught. So what do we think is going to happen to an initially rare infectious disease close to our disease-free equilibrium if this disease-free equilibrium is unstable? Yes?
So if R naught is over 1, then if it's unstable, I assume it's going to actually spread over time?
Exactly. Yeah. So we're going to have this, in fact, early exponential growth of an infectious disease. We're going to have an epidemic, in other words. Okay. That's what it really means for our disease-free equilibrium to be stable in this context. Okay. So an epidemic. In other words, the disease will spread. So this quantity here that we've introduced, R naught, is very common. Who's heard of R naught before? A few of you, great. This is the basic reproduction number and tells you the expected number of infections or the average number of infections that you would get caused by one infected individual when everyone else in the population is susceptible. So intuitively, if this R naught is greater than 1, like we had on the previous slide, that means that one infected individual is going to give rise to more than one infection on average. And each of those people early on are going to give rise to more than one infection on average. The number of infections is going to grow exponentially. Whereas if R naught is less than 1, people are infecting less than one person on average. Therefore, it's going to decay away to 0. This R naught is really important in epidemiology. It also turns out that when it comes to evolution, it can sometimes tell us something about how we expect pathogens to evolve. Okay, so it is sometimes, crucially not always. We're going to gloss a little bit over the not always thing because it gets a little bit complicated, but it's not always, but sometimes a measure of a pathogen's evolutionary fitness. Okay, so we're going to see why that's the case. So that's all of our epidemiology or ecology. Now we're going to think about evolution, okay, in the context of this pathogen. And just to make sure it's clear, from now on, we're going to be thinking about our endemic equilibrium. Consider. Note, from now on, S star, I star refers to our endemic equilibrium. Okay, so we're moving on from our disease-free equilibrium. We found a condition that allows our pathogen to spread. If we want to think about how our infectious disease is evolving, we obviously need the infectious disease to be present in the population. Okay, so we're only going to consider scenarios where it is actually viable and can spread. Okay. It is possible as well to show that this, when R naught is greater than 1, this is locally asymptotically stable, this endemic equilibrium. Again, I'll leave that as an exercise for you. It gets a little bit messy. I really want to focus in on the evolution here, though. Okay, so we're just going to take my word for it that it is locally asymptotically stable. Okay. What we're going to do is the same as we've done before. We're going to consider the invasion dynamics of a rare mutant pathogen, trying to invade this endemic equilibrium. Okay, so there's already a pathogen there. We're going to say, okay, there's a mutation that occurs, just like we have, with COVID and things like that. A mutation occurs, a new variant of concern arises, perhaps. And we're going to see if this can spread. We're going to assume that it has virulence. Its mortality rate is going to be alpha sub m, and it's going to have population density I sub m. Moreover, we're going to assume that more virulent pathogens are also more transmissible. What this means then is we're going to set our transmission rate beta to actually be a function of alpha. And because we're assuming that more virulent pathogens are also more transmissible, this means that beta prime alpha is going to be positive. Why might we do this? Well, one of the arguments here is that pathogens have to infect host cells and tissues in order to transmit, in order to replicate within the host, in order to grow and produce new transmission stages. Therefore, if they're not infecting many host cells, they're probably not going to be very transmissible, but they're also probably not causing much damage. If they're able to infect lots and lots of host cells really quickly, then they're probably causing a lot of damage to their host. So the virulence will go up, but they're also producing more transmission stages. So there should be some positive relationship between these things. Okay, so based on our earlier equations, if we just go all the way back up to the beginning, this is my di dt here. We now need to think about what are the invasion dynamics for this rare mutant. Okay, so they look very similar initially to our resident population. But now we're going to have our mutant, IM. So the I's get replaced with IMs. We have our host population is at its equilibrium, S star. We've also assumed in this particular model that there's no recovery, so I'm just going to get rid of that gamma. And then the last change here is that this pathogen has a slightly different level of virulence, alpha m. Incidentally, I talked a little bit, this idea of this relationship between beta and alpha is an evolutionary trade-off, and we'll talk more about this on Wednesday next week as well. Okay, so just like before, we can calculate our invasion fitness of this rare mutant. So we don't have to look at our next generation matrix for this example because there's just one equation here, right? We have IMs appearing in both terms, which is nice. So we can think about its per capita growth rate when rare, we divide through by IM, okay? So its invasion fitness, W. This W, its invasion fitness is a function both of the trait of our mutant, alpha M, and the trait of the resident population, alpha. And it's going to be its per capita growth rate when rare. So we divide by IM. Then we take our equation from the previous slide. So here we can have beta of, oh, sorry, I've missed out something up here, I realize. Apologies. This should be a beta of alpha M. So we have a beta of alpha M times by S star minus D minus alpha M. Any questions so far? Nope. Okay, we've done this process a number of times, right, with our, particularly with our specific competition model. We find our ecological dynamics, we check its stability, which we kind of glossed over here because it's kind of laborious. We're jumping straight to the evolutionary steps. we find our invasion fitness. Next thing we need to do is find our selection gradient, right? This is going to tell us the direction which our traits are going to be evolving in. So our selection gradient, S of alpha, in fact, because we've got an S in this model, it's a little bit confusing. I'm going to make this a lowercase s to make sure it's distinct from our density of susceptibles, okay? So this is our selection gradient, not our density of susceptibles. So S of alpha is just going to be our partial derivative of invasion fitness with respect to our mutant trait, alpha m, evaluated when alpha m is equal to alpha. Okay. Like I said, this is exactly the same as the process we've done before with intraspecific competition. We find our invasion fitness, we find our selection gradient, find our singular strategies, and think about the stability of those singular strategies. Okay. So what does this look like? Well, we can take our derivative of beta with respect to alpha m, and then substitute in alpha m is equal to alpha. This just gives us beta prime of alpha. S star is a function of alpha, so it's just treated as a constant. The d drops out, and we end up with a -1, which is taking the derivative of alpha m with respect to alpha m. Okay, this is just linear and alpha m at the end. This is our selection gradient, and therefore our singular strategy must satisfy what? Can anyone remind me, when do we get a singular strategy? Yep, selection gradient is equal to 0. So some alpha star must satisfy S of alpha star equal to 0. This occurs, therefore, beta prime of alpha star times by S star is equal to 1. Nice and simple. Okay. What about our evolutionary stability? Remember, this is telling us if our trait at our singular strategy is uninvadable. Okay. This is going to be our second derivative. Remember, we usually call this capital E. It's our second partial derivative, second order partial derivative of invasion fitness with respect to our mutant trait. And then we evaluate all of our alphas at this singular strategy alpha star. This is just going to be the second order derivative of beta evaluated at alpha star times by S star. And what does this need to be if this is going to be evolutionarily stable?
Less than 0.
Less than 0, exactly. Can anyone remember why it's less than 0? The sort of intuition here is? Yes?
Fitness maximum.
Exactly. This is telling you about the curvature, right? So just like any function, if you take its second order derivative, it's going to tell you about the curvature. Okay, if you've got a turning point, it's going to tell you if it's a maximum or a minimum. So this is telling you this is a fitness maximum, therefore it can't be invaded. Okay, so how must our transmission rate change with virulence to guarantee evolutionary stability? Can S star be positive or negative? Well, it has to be positive. It's population density, right? So this has to be negative, right? So what does that look like? Well, let's think about sketching a graph. We need our second order derivative of beta to be negative. So maybe it looks something like this. Got beta of alpha versus alpha. In the region of our singular strategy, it needs to be concave down. So let's suppose this is my alpha star here. At this point, my trade-off has to be something like this. This is important because intuitively it tells you something about the relationship. Ultimately, these are biological processes, right? This is virulence, this is a mortality rate. This is a transmission rate. Tells you something about how the transmission rate must be changing with virulence in order to get a singular strategy that is a fitness maximum. In other words, an optimal level of virulence. What's going on here? Well, as we increase alpha, the mortality rate is increasing. But because we're concave down, it means that there are diminishing returns in terms of transmission. So from a pathogen's perspective, it doesn't want to kill its host, right? Want in the sort of, if it had a choice. But it has to have a certain level of virulence in order to be able to transmit, to replicate within that host, okay? But there's going to be a point where it's just causing so much damage to its host that it's not able to produce sufficient transmission stages. It's going to be some limit. Maybe it's actually producing those transmission stages, but the host is so sick that they can't go out and meet anyone. Okay, so it's debilitated them to the point where they're not actually able to transmit. Okay, so there's diminishing returns. There's a key concept here sometimes with trade-offs. Okay. Time is a little bit short, so what I'm going to do is I'm going to jump and talk through these notes rather than writing everything out. So what we've done is gone from this slide here to the next one. So we need to also, we've got something about evolutionary stability. We need to think about our convergent stability as well, right? So we take our cross derivative, our second order cross derivative here of invasion fitness with respect to our mutant trait and with respect to our resident trait alpha. We evaluate everything at our singular strategy alpha star. What does that look like? Well, we've already earlier, when we were working out our selection gradient, essentially calculated our partial derivative with respect to alpha. So now we, with alpha m, sorry. Now we take this term in the middle, beta prime alpha m times by s star of alpha. I've called it s star of alpha just to make sure it's explicit that this is a function of alpha. In other words, our density of susceptible hosts at equilibrium is determined by the virulence of the pathogen, okay? And -1. We take the partial derivative of this with respect to alpha, and we evaluate then all of this at alpha star. This is just application of the quotient rule because our beta prime of alpha m is going to be a constant out the front. We're at our endemic equilibrium, and this is s star of alpha is alpha plus d over beta of alpha. So we need to use our quotient rule. This should be relatively straightforward. When you do this, you end up with a beta prime alpha star at the front over beta of alpha star. And then this term in the middle is just our selection gradient. But we're evaluating our selection gradient at alpha star. And by definition, alpha star is our singular strategy. So our selection gradient has to be equal to 0 here. So this term in the brackets just goes to 0. Therefore, our cross derivative is equal to 0. Now, if you remember your convergent stability, C is given by this cross derivative plus our evolutionary stability. So essentially, our convergent stability, our C is equal to E. That means that if our singular strategy is evolutionary stable, it is automatically convergent stable. If it is evolutionary unstable, it is automatically convergence unstable. So that means that we can only have 2 types of singular strategies. Remember, we have 4 possible types of singular strategies based on the signs of these E's and C's. If E and C are both negative, we have to have a continuously stable strategy. This is our fitness peak, and there is a path that leads us all the way to that fitness peak, right? We converge to it. And once we get there, it's uninvadable. If E and C are positive, then we have an evolutionary repeller. This is like our valley, right? Everywhere around has a higher fitness, and we just move away from it. Okay? We can't get branching points with this because these have to have the same sign. We can't get a Garden of Eden with this because they have to have the same sign. Yes.
So you said C equals E in this case?
Yes.
But isn't the cross derivative, like, I don't understand why it's 0 because I'm just saying, isn't the second term inside the parentheses of 0? We still have a 1 left over, so.
Sorry, this is a little bit of confusion here. I can see where that's come from. Let me just, this is the problem of using susceptible and infected models because we have S's and we typically refer to the S as our selection gradient as well.
Oh, right.
This is our little s, which is our selection gradient.
Right, right.
So this is this S star of alpha star. Big capital S is our density of susceptibles at the equilibrium. This little s of alpha star is our selection gradient. I appreciate that wasn't clear though. Thank you for pointing it out. Okay. Let's then think about, I mentioned R naught earlier as being an important concept in epidemiology. Also tells us sometimes something about evolution. So let's think about what our R naught looks like. So our R naught in this model with a trade-off is going to be beta of alpha times by S star over alpha plus D. Now this S star we would typically take as being our disease-free equilibrium, right? Because we're thinking about R naught is the invasion of infection into a population. There's a different S star from what we had on the previous slide, okay? So let's think about just what happens if we differentiate this reproduction number with respect to alpha. Again, we've got alpha in the numerator and denominator, so we need to use our quotient rule. We take dr naught d alpha, S star just comes out the front, doesn't actually matter here. We end up with this term in the middle. And so let's think about when is this R naught possibly maximized? Okay, for this to be possibly maximized, the numerator in this bracket has to be equal to 0, right? Because we're at a turning point for our R naught. So let's think about when is this equal to 0? We set this equal to 0. Well, let's take out a factor of beta alpha. Let's take this up the front. We now have an alpha plus D over beta alpha times by beta prime of alpha minus 1. To avoid confusion as before, let's just make sure this is a little s. This is our selection gradient. This is our general selection gradient, but if we think about what happens at S star, S of alpha star, so we pick an alpha where our selection gradient is equal to 0. In other words, we're at our singular strategy. That means that this is going to equal 0. And therefore, our R naught is going to, dr naught, dr alpha is going to equal 0. In other words, our singular strategy, alpha star, is not only a maximum for our invasion fitness, it's telling us that this is a sort of an optimal strategy. It's also maximizing R naught. It's maximizing the initial growth of infections. It turns out that you can do this as long as there are certain feedbacks and structures not in the system. You don't necessarily even have to go through all of that adaptive dynamics. Sometimes you can just look at R naught. And R naught is pretty simple to calculate. To calculate R naught, if you recall, all we had to do was, which is actually an even simpler way of doing this. Let's go back to my equations here. To calculate R naught, you just have to look at when is this equation here positive for small values of I. If you do this inequality and rearrange it, you'll get R naught. So this is one of the really cool things sometimes about infectious diseases. We learn something quite fundamental here, that that evolution by natural selection is actually maximizing R naught. Again, this is not always the case, but in this relatively simple example, it is the case. These two things happen to coincide, their maximums coincide. They're not the exact same equations, but their maximums coincide. Okay, so just to recap what we've done today, we've covered quite a lot of ground today because we've had to introduce these infectious disease models. We've gone relatively quickly over summarizing their ecological or epidemiological dynamics, talked about the basic reproduction number R naught. I would encourage you to use this as an example for practice in your own time. You've got the answers there of these are the equilibria. Have a go at finding those equilibria just to make sure you remember how to do this and checking that they're stable, or at least the endemic equilibrium is locally asymptotically stable. We've then done this first very simple model of pathogen evolution. And it's told us a few fundamental things. It's told us that there must be some key relationship between our rate of virulence, our mortality rate, and our transmission rate. This is this curve up here. In order to get some optimal level of virulence for a pathogen, we need to be having a curve that looks like this, some relationship between transmission and virulence that looks like this. If this curve curved up, if it was concave up, it would not be evolutionarily stable. You'd be able to find a singular strategy, but it wouldn't be evolutionarily stable. It would be a repeller. Okay, so that would mean your virulence would either go down to 0 or it would go off to infinity, depending on which side of that repeller you are. Like I said just now, in this particular example, because there is no structuring in the population, and structuring in a particular sense, we're pretty not going to get time to go through this in this course, but I just want to make sure it's clear that this is not always the case that it maximizes R naught, okay? But in many cases, it does. So we can actually see parallels between sort of the initial spread of infection and also what evolution maximizes. Okay, any questions? If not, I have office hours now until 12:20. Other than that, I'll see you on Wednesday. Thanks.